Hello, everybody, and welcome back to Pre-Calculus with Mr. Beck. As we continue our journey through mathematics, remember, I've got your back and you've got your back. What we're looking at today is day 2 of our 9.3. 9.3 talks about DeMoivre's theorem. What we did in day 1, we really went through all of the different skills of like setting up the ideas behind DeMoivre's theorem. Today, we're actually going to get to apply them. We are going to do a little bit of review, and I also want to go into a little bit more depth. Last time I really wanted to focus on the skills needed for what we're doing today. Today, I really want to tie these concepts together as closely as possible. So going into what is a complex number. If you remember, a complex number, which we write z, is in the form of either a plus bi, but it also can be written in the form of x plus iy. The reason why we use x plus iy is because that x ties into the real axis, and iy on our normal y-axis, we are going to change it into the imaginary axis. Now, a big feeling for me, I really don't like calling it the imaginary axis, but at the same time, imaginary has stuck, and so let's be consistent with the mathematics. Just because these are complex numbers, just because we say they're imaginary, they're not actually imaginary. Believe it or not, they are real, or shouldn't even say real. We don't want to call it imaginary because that a lot of people think it doesn't exist. Complex numbers are used very, very extensively in electrical engineering. So these have a big purpose. So we're setting up a lot of the ideas behind, for those of you who are going into engineering, what you're going to be doing with that. So if you remember, we said this complex number, this x plus iy, if we plotted it, we kind of merged the ideas with polar that we said, hey, that distance is called the radius. Now, if you remember, that radius is x squared plus y squared. Okay, fair enough. But this really has another name. Another name for the radius is called the modulus. And the reason why it's called the modulus is because we're now talking about complex numbers. We really want to know how far that modulus is, or how far the complex number is away from 0. Now, a lot of the ways that we could, or one of the ways we could think about modulus is by the name magnitude. The magnitude of a number is really what we consider its absolute value for at least real numbers. So for instance, the absolute value of -3 is 3 because this is the distance from 0. So the distance from 0. If we say the absolute value of 5, that number is also 5. Well, if we say, what about the absolute value or the magnitude of I? Well, if you think about I as being 1 unit up on the imaginary axis, that should be 1. Well, then we start coming into what happens if we say something a little bit more complex, which would be, let's say, x plus iy generically. What we would do is we would have to use the distance formula, square root of x squared plus y squared, because it's that horizontal distance, that vertical distance. And again, this is where it ties back into all the work we've done in polar. This is an application of that polar by saying the modulus or the magnitude or the distance from 0. When we say from 0, this is the true 0 number. Even though it kind of looks like it's the pole, this is the true 0 number. So really, we should call this the magnitude or the modulus, to be more specific. Now, the modulus, we kind of note it as, it looks like the absolute value of z, but it's really the magnitude of z. And then theta is going to be what we call the argument. And I'm saying this more for, let's just be a little bit more precise in our terminology of it. A lot of people will understand that theta is really going to be just that theta off the real axis, but it's officially known as our argument. So on to a little bit more review. If you remember last time we talked about multiplying complex numbers, we said if we multiply those complex numbers, what would end up happening is their magnitudes, we said radii last time, but their magnitudes will be multiplied and their angles will be added. Now, I wanted to show that one more time, just because, again, my goal for today is to let's connect as many of the ideas as we possibly can. So what I'm going to have you do first is take this first complex number, this zi, or z1, and let's turn it into rectangular form. Now, to turn it into rectangular form is actually the easier approach, because what we know is this cosine of 2 pi over 3, that is in quadrant 2, and the cosine of my pi over 3 is a half. So z1 ends up being 3 times negative a half. And then, again, quadrant 2, sine is positive, so plus I, and signs are square root of 3's over 2. And then let's go ahead and distribute. That is negative 3 halves plus 3i square root of 3 all over 2. Let me zoom in just a little bit more. And z2. Z2 is 2 times cosine of 5 pi over 6. 5 pi over 6 is going to give us negative square root of 3 over 2 for the cosine. And then for the sine is a positive 1/2. Let's write it this way. So multiplied through, we end up with just negative square root of 3 plus 1i. Now, if I multiply these two together, remember we're going to take our traditional FOIL approach. So first outer, inner, and then last. So traditional FOIL approach. The first is going to be a positive 3 square root of 3 over 2. The outer will give me a negative 3 halves I. The inner is going to give us a negative 3i square root of 3 times the square root of 3 over 2. And then the last will be a positive 3 square root of 3 over 2i squared. So again, foiling through, we get this. Now let's clean it up a bit. First term is still 3 square root of 3 over 2. The second term is still negative 3 halves I, so not much cleanup there. This third term is going to be the square root of 3 is multiply. We have 9 halves I. And then the last one, if you remember, I squared is equivalent to negative 1. Since I squared is equivalent to negative 1, and by the way, we're going to explore that a little bit more today, that ends up multiplying it by negative. And now, if you notice that this 3 square root of 3 over 2 and this negative 3 square root of 3 over 2 will cancel each other out. These two we can combine together into negative 12 halves I or negative 6i. So what ends up happening is when we multiply these two together, we end up purely with negative 6i. And so let's look at that on the polar level. So on the polar level, if we multiply the two radii together, or the two moduli together, 3 times 2 is 6. So z1 times z2, multiply those two together. We have 3 times 2. And then let's add our angles, which by the way, that's 6. If we add our angles, 2 pi over 3, and then plus 5 pi over 6. Adding these together, common denominator, we end up with 9 pi over 6, which is 3 pi over 2. So multiplying them together, we end up with 6 times cosine 3 pi over 2 plus I sine 3 pi over 2. And if you notice, that ends up giving us cosine of 3 pi over 2 is 0, sine of 3 pi over 2 is negative 1. We end up with the exact same thing. So when you look at it and you say, what approach is going to be better for us for this problem? I would say the polar is definitely a lot more efficient with this problem. Again, my goal is to make connections. So we are going to be doing some multiplying. When we do the multiplying, I wanted to show you at least once. I have the calculator off to the side over here. This calculator is set to its complex form so that it can perform those complex operations. And I'll do the multiplying in that calculator just to speed up our video. So let's finish up. And if you notice, I had to I had a few technical difficulties. I couldn't move my screen for whatever reason. So let's actually show this. The angle of 2 pi over 3, we do know right here. So this was my Z1. Z2 ended up being cosine of 5 pi over 6. So we had 2 pi over 3. And then we also have 5 pi over 6. So if we start there and we go 5 pi over 6, this is 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6. So if we add our angles and then we multiply our radii, we end up with right here. So this is just kind of like a quicker approach to or at least showing that graphical relationship. All right, on to, let's set up DeMoivre's theorem just a little bit more. So if you notice with problem number 2, I have Z1 is negative square root of 2 plus I square root of 2. So what I'm going to do, this is where I'm going to use my calculator. I'm going to say, what is negative square root of 2 plus I square root of 2? And multiply that out 3 times. Negative square root of 2 plus I square root of 2. So let's go ahead and type it out. So negative square root should be right here. Negative square root of 2. And then plus, now we can't just actually put in the letter I on this calculator. If we put in the letter I, it won't be bolded. This is bolded, which actually represents that it is that complex number, the square root of negative 1. So plus I square root of 2. And let's multiply that by itself times. This is a little bit annoying, but at the same time, helpful to see. A square root of 2, and honestly, probably still saves time from having to multiply it out ourselves. Plus I square root of 2. Let's multiply that, and that ends up multiplying to be negative 4i. And so I'm going to multiply that answer by, once again, you guessed it, square root of 2, square root of 2, and then plus I. And there's so many ways I could have been more efficient with this, but I'm just pushing forward right now. So I square root of 2. And that should have been negative. Glad I caught myself before I went too far. And we get this answer of 4 square root of 2 plus 4 square root of 2i. So this is 4 square root of 2 plus 4i square root of 2. Now, let's convert this to polar form. So first of all, negative square root of 2 plus I square root of 2. If you remember to do our conversion to polar form, first thing is we need to know our radius. Our radius is the square root of negative square root of 2 squared plus square root of 2 squared. So that x squared plus y squared. So we get the square root of 2 plus 2, square root of 4, which is just 2, convenient. And then our angle, or our argument, to be more specific, our argument is going to be the inverse tangent of the y value over the x value. Now, this is in quadrant 2, and the reason why that's important is because the inverse tangent of negative 1, but that angle in quadrant 2 is 3 pi over 4. So our radius, or our z, our complex number, is 2 cosine 3 pi over 4 plus I sine 3 pi over 4. So if we take this and we multiply by itself one more time, so if we multiply by itself, and this is where I'm also going to do what we call the shorthand. Because this gets really, really annoying writing the cosine plus I sine over and over again, we actually can write this as what's called cis. Cis represents cosine plus I sine. Now the reason why we write cis is because those angles are always going to be the same, at least for all of the complex numbers we're working with. Because those angles are always going to be the same, we're just going to call it cis. So if we take this times 2 cis 3 pi over 4, those two multiplied, we will multiply the two radii together to get 4. And then if we add the two angles together, 3 pi over 4 plus 3 pi over 4 is 3 pi over 2. Now, just as a quick check, concept-wise, the cosine of 3 pi over 2 is 0. And then the sine of 3 pi over 2 is negative 1. And if you notice, we get that negative 4i, and somehow this moved over, but we get this negative 4i, which multiplying them together is what I have here. That's what's supposed to happen. So if I multiply this by 2 cosine plus I sine of 3 pi over 4 again, we are going to have 4 times 2, which is 8. And then cosine plus I sine, we have 3 pi over 2 plus 3 pi over 4, plus 3 pi over 4. So 6 pi over 4 plus 3 pi over 4 is 9 pi over 4. So 8 cosine plus I sine of 9 pi over 4. Now, just as one more quick check, and this goes back to converting, the cosine of 9 pi over 4, 9 pi over 4 is coterminal with pi over 4. So the cosine of pi over 4 is square root of 2 over 2. And then the sine of pi over 4 is also square root of 2 over 2. Multiplying those two together, we get 4 square root of 2 plus 4i square root of 2. Once again, that's what we have in the calculator here. So I feel like I'm on the right track. And that's the important thing because it's just trying to get this general idea of how does this all work. Now, I know some of you probably are sitting here listening going, wow, he spent way too much time on that kind of problem, because if we are multiplying it 3 times, can't we just right from the beginning, couldn't we have just said z is 2 times 2 times 2? And then I'm going to go ahead and put the cis again. And then rather than say 3 pi over 4 plus 3 pi over 4 plus 3 pi over 4, couldn't we have said that this is 3 pi over 4s? And speaking of which, if this is 3 2's multiplied, we can write that as 2 cubed cis of 9 pi over 4. That would make life a heck of a lot easier. And what do you know? That's exactly what DeMoivre's theorem says, that if we are taking a complex number and we multiply it out multiple times, then what happens is we could take our radius to that power, and then our cosine plus I sine, we can just multiply. That's probably better seen right here. We could just multiply those angles, or the argument, by how many times we're multiplying by. So makes life a heck of a lot easier. And that's why DeMoivre's theorem is so important. So really, DeMoivre's theorem, at least the portion we're going to work with right now, DeMoivre's theorem is all about simplifying that multiplication if we have to do it many, many times. So let's actually apply it. So if I have z as this in our polar form, life is great, because what we end up doing is just saying z cubed. We will take our radius, cube that, and then I'm going to go ahead and write this in cis form just because it's so much more efficient. So 3 times pi over 3, and 5 cubed is 125, cis of pi. Now, this is going to be our standard that if we end up with an angle that we know, we do want to convert that, that polar form into rectangular form, just because it gives us more of a context of what we're familiar with while still linking the polar ideas together. So the cosine of pi, let me go ahead and write this out. This is probably be the last time I'm going to write this out in detail. This is cosine pi plus I sine pi. And if you remember, the cosine of pi is -1. So negative 125. And then the sine of pi is 0, so plus 0i. Yeah, we could just leave that as negative 125, but negative 125 plus 0i. Z to the 6th. Z to the 6th then would be 5 to the 6th, cosine plus I sine of 6 times pi over 3. So that ends up giving me 5 to the 6th, and I actually don't know what 5 to the 6th is off the top of my head. I'm just getting a math teacher, and I've done this many times, but 15,625, 625, and then cis of 2 pi. Everybody, that is an angle that we know. So the cosine of 2 pi is 1. So 15,625 times the sine of 2 pi is 0. So plus 0i. Now, if you want to think about it, and this is where we're starting to build some relationships, in order for me to go from z cubed to z to the 6th, what I could have done is I could have just said this is negative 125, the result that I got from here, squared it, and if you notice, that number is just 125 squared. So, and again, this is all about building the relationships between real and complex numbers and how they're working kind of on that polar, or on that, really on the polar level. So z equals -3 plus 0i. Once again, I'm trying to take a concept of, do we know what z squared is? Yes. What is -3 squared? -3 squared is 9. Okay, I know the answer, but I don't really care about the answer. I'm trying to care about what are the details that go into that answer. So what I would like to do with this is I'd like to first convert this into its polar form. So -3 plus 0i, if you look at where that is on a graph, Negative 3 plus 0i would be right here. So the radius on that one is 3. And what angle does it take to get there? That would be pi. So 3 cis pi. If I take 3 cis pi and I square it, that ends up giving me 3 squared cis of 2 times pi. Remember, this is where we're using DeMoivre's theorem. We're taking our radii to that power, and then we're multiplying our angle by that power, which gives us 9 cis of 2 pi. Now, cosine of 2 pi, once again, is 1. 9 times the sine of 2 pi, 9i times 0, that just gives me 9. Once again, it's that connection of how does the real number and the real number system and the complex number system, how did they really combine together into one? Everybody, what is negative 3 to the 4th power? That should be 81. Let's see how that applies if we use DeMoivre's theorem on it. So 3 cis of pi, if we take that to the 4th power, that would be 3 to the 4th, and then cis of 4 pi. And once again, 3 to the 4th, 81. Feel like we're on the right track here. Cosine of 4 pi. If you remember, 4 pi is coterminal with 2 pi and 0. So that ends up being cosine of 0 plus I sine 0. I really should have left that as 4 pi, and I told you that was the last time I was going to do it. So anyway, the whole point is that just gives us 81 again. So on to the next one. What happens if we only have a complex or imaginary portion of this? So what I'm going to do is I'm going to try to simplify things just a little bit. That 0 plus I we do know is right up here, and that angle should be, or that argument should be pi over 2. So this can be written as a radius of 1 cis of pi over 2. So what happens if I square I? So I squared, we said was negative 1, and I kind of teased you earlier that you were going to explore this in a little bit more detail. So I squared, we said was negative 1. Well, if we take 1 cis pi over 2 and we square it, that's equivalent to 1 squared cis of 2 times pi over 2. So that is 1 cis pi. Now, if I want to take this and say, where is that located? The radius is 1 and the angle is pi. So that makes sense that it's only on the real plane of negative 1. More importantly, let's go numerically on this side. Cosine of pi is negative 1. The sine of pi is 0. And so we get that negative 1. So for those of you who do know me in person, I am all about the Triforce of mathematics, the graphical, the algebraic, and the numeric. Combining all of these together into one with polar and complex numbers is amazing. Well, what about z to the 6? Remember, this number is I to the 6, and if we learned in Algebra 2, we said, oh, I to the 6 was I to the 4th times I squared, so that's 1 times negative 1, so this should also give me negative 1. Let's see that on a polar level. So on a polar level, z to the 6 would be 1 cis pi over 2 to the 6th power, which is 1 to the 6th cis, 6 times pi over 2. So that's 1 cis of 3 pi. And 3 pi, if you remember, is coterminal with pi. So really, this is just going to give us the exact same answer that we had before. So 1 plus 0i, or just negative 1. All right. So what I'm really hoping is that you've kind of made this connection of why or where DeMoivre's theorem actually, or how it can be applied. Now, we like this because it does make things a little bit easier. Obviously, in these problems, I made them more complex. Again, pardon the pun on that one. I made it more complex just so I can build those connections together. Let's actually apply this to something that is a little bit less known. So on problem number 7, what I have here is I have this complex number that the radius of it, or the modulus of it, is the square root of 2, and our argument is 5 pi over 16. So just to kind of take a look at where we are, we're not that far off of 0, and 5 pi over 16 is just a little bit more than pi over 4. So let me draw that a little bit more appropriately. We're probably about right there. Now I want to take that number to the 4th power. First, we're finding z to the fourth. So actually, I don't think that one's supposed to be there. Let's just go ahead and find z to the eighth. So if I want to take this complex number of square root of 2, I'm going to write this as cis 5 pi over 16. If I want to take this to the eighth power, this would be the square root of 2 to the eighth power, and then cis of 8 times 5 pi over 16. The square root of 2 to the eighth, if you remember, we have 2 to the 1/2 to the eighth. Cis of, these will reduce, 8 and 16, 1/2. So cis of 5 pi over 2. So if we multiply our exponents right there, that gives us 2 to the fourth. So 2 to the fourth, cis of 5 pi over 2. 2 to the fourth is 16. We can leave it maybe as cis 5 pi over 2, but this is a known angle, so let's go ahead and put that into rectangular form. The cosine of 5 pi over 2 is 0. The sine of 5 pi over 2, 5 pi over 2 is coterminal. Probably should have done this a while. This is coterminal with pi over 2. So we simply get 16i. So 16i, very, very nice answer for a very, very ugly looking problem. And on to the last one for this video. The square root of 3 minus I to the 6th power. Now, a lot of times when I give this problem in the class, I have a lot of students who say, oh, I'm going to FOIL this out or multiply this out a total of 6 times. And so I have them do that. And in the end, I personally prefer just to use the polar form on this. So our first goal is, let's get this into polar form, or our cis theta. So our radius is going to be the square root of square root of 3 squared plus -1 squared. Remember, we're not squaring the I, we're squaring the Y value. That's a common mistake that students make. So this would be the square root of 3 plus 1, or 2 again. And our argument, our theta, is going to be the inverse tangent of Y over X. Now, we usually see that as negative square root of 3 over 3, but the important thing is, what quadrant are we in? The X is positive, the Y is negative, so we are in quadrant 4. So what is the inverse tangent of negative square root of 3 over 3, but in quadrant 4? That looks to be, I like to draw this out. We're down here. So everybody should realize that is 11 pi over 6. So 11 pi over 6. So our complex number is really 2 cis of 11 pi over 6. We take that to the 6th power. That's equivalent to 2 to the 6th cis of 6 times 11 pi over 6, or 2 to the 6th is 64 cis of 11 pi. Now that's a number that, or that's an angle that I know. This is coterminal with pi. Since that's coterminal with pi, that would be 64 times -1. Cosine of pi is -1. Sine of pi is 0. I think we've done that a few times now. -64. Now, one last thing on this problem. Somebody usually asks in my class, I always go with the 11 pi over 6 just because that's the angle that we're more familiar with. Somebody always asks, Mr. Beck, could we write that as negative pi over 6? I'm like, let's try it. Let's see what happens. So if we said this is 2 to the 6th cis of 6 times negative pi over 6, we end up with, again, 64 cis of negative pi. Now, negative pi, once again, is also coterminal with pi. So we are still going to get that answer, -64. It's always a great question. I love making those connections with everybody. So this will be the end of video 1. We talked about DeMoivre's theorem in terms of multiplying it out. So I'm going to go ahead and stop this and ready for us to work with complex roots in video number 2.